All right, so today we're going to have a look at the photon model. And this model, it says that light is not only waves. So that's what we've been looking at. We've been looking at the wave structure of light, but it can also interact like a particle. So we actually see photons interacting in the same way as you'd expect like an electron or a proton or a neutron. So this is the photon model. Now photons, when they're interacting with matter, we say they behave like particles. And this is different to what we've been expecting. And it's not really something you think of instantly because let's say if we go outside and we're standing in the sun, if we were being acted upon by particles, you'd think we'd feel it. It'd feel like we're getting hit by hail or something because all those light, if that was particles, they would be bombarding us. But we actually do see that. And what we do is we call these particles photons. So although this isn't directly obvious to us just by thinking about it, it does happen. All right. So what proof do I have that light isn't just waves? So if we have a look in the bottom corner, we see what we see here, the bottom right, is the two slit diffraction buildup. So remember when we put out light through our two slits, we saw these bands of light. All right, but what happens if we do that and we don't expose it to a laser or to a sodium lamp, but we expose it to a really, really low level light? What we see here is in the top right, this is the first image we took, and you can see we're just seeing some random dots there. Okay, now if we leave that for a little bit longer, so we're in a really, really low intensity light, we leave it for a long time, we see some more dots starting to build up, and we still really can't see a pattern, but we'll move on. You can see here, by the third time, we can see we're getting these stripes. And the interesting thing about this is we're beginning to, looking at the fourth one, we're beginning to build that exact pattern that we see with two slit diffraction. And moving forward, we almost see it perfectly in the last one. We see that perfect double slit diffraction. So the reason that this behaves as particles is because we see those individual spots building up. If we acted like a wave, we'd instantly see this final one. But because we see this building up of the individual spots, we say that this is a proof that it acts like a particle. It's also proof of the particle wave nature acting together, because although we do see the particle build up, we also see in the end we see this wave pattern that can only happen from a wave. Okay, so if we say that photons are particles, they have to have some energy and some momentum. So what we say is, for the first equation we've got is for energy. We say that energy E equals HF. Now, easy way to remember it is my initials are HF, so this is one of my favorite equations, but that's just a bit of a side. And the second one, momentum, P, remember P is for momentum, equals H on lambda. Now, we've seen this lambda before, and we've seen this F, but what is this H? So H is Planck's constant. It's just a constant value, constant meaning it never changes. The value of it is 6.63 times 10 to the negative 34. All right, and 6.63 by 10 to the negative 34, that unit for that also is joule seconds, so JS. Now, F, we saw in that equation as well, that's the frequency of light, that's measured in hertz, and the wavelength is measured in meters. Okay, just a quick reminder that energy is measured in joules. We can also measure that in electron volts. And our momentum is measured in kilogram meters per second. Okay. Or newtons per second. All right. So those are two equations that we're going to use a bit very frequently throughout this next chapter. And that is actually not correct, sorry. It's sec newtons, we remember. I don't know why I did that. But yeah, those are the units and all of the things we need for these two equations. So let's have a look at a really quick example. So calculate the energy in joules and electron volts, as well as the momentum of orange light, which is wavelength 600 nanometers. So the first thing we want to work out is the energy. So E equals HF. So we also want to work out the momentum, which is H on lambda. Now, what we know from here is that the wavelength equals 600 nanometers, which is times 10 to the negative 9 meters. And we know that h equals 6.63 by 10 to the negative 34. So because we know that Planck's constant and the wavelength, what I'm going to do is I'm actually going to work out momentum first. So this thing equals 6.63 by 10 to the negative 34 divided by 600 times 10 to the negative 9, which equals 1.11 by 10 to the negative 27 sec newtons. So next we have to work out energy. We have E equals HF. But the thing is, the problem we've got is we don't know what the frequency equals. All right, but we do have this equation, the wave equation V equals F lambda. Remember that one. So what we need to do is we need to first establish that V, in this case, is the velocity. It equals the speed of light because we're talking about orange light. So V equals C. And the next thing we want to do is we want to rearrange this equation. So we want to work out the frequency. So if I divide through by lambda, I'm left with V on lambda or C on lambda. Okay, substitute that in. C is 3 times 10 to the 8 and lambda is 600 nanometers. Okay, and that will give us a frequency of 5 by 10 to the 14 hertz. So now we know the F, we know our Planck's constant, so we can just put this straight into the equation. So our E equals 6.634 times 5 by 10 to the 14. Oops, I just forgot that 10 to the power of negative 34. If you multiply those together, you get 3.32 times 10 to the negative 19 joules. Now, if I divide that by 1.6 by 10 to the negative 19, I'll get my answer in electron volts. So either 3.32 by 10 to the negative 19 joules or 2.078 electron volts. All right, so that's basically how we use those two equations, and hopefully we can have a go at those now.